What is calculus? Well, ultimately, the root of calculus comes down to these two pictures. So, rate of change. Now, rate of change is something that you probably learned as early as grade 9, which is what is called slope. The thing is, if I ask you to find slope between 2 points on a graph like that, and those points are distinct, they're different, finding the slope between those 2 points is not a difficult challenge because you just do rise over run. So you can draw a little triangle here, and you can do rise over run. And this allows you to calculate how fast the function is changing for a given time or space interval. Now, what happens if you wanted to find the rate of change of something, but this time is just at a point? So this here is a difficult calculation and really is the beginning of calculus. So it wasn't presented this way necessarily, but people like Newton and Raphson, and there are claims that even ancient people had come across this type of dilemma of how do you find the instantaneous rate of change or the change at a given point on the graph. Geometrically, this rate of change here, or slope, is of a line that is called a secant. A secant is a line that touches a graph twice, like that. See how it hits the graph twice? It could hit it more than twice, but we're just interested in these 2 points. Finding the slope of a secant is an easy calculation, and we're going to review that calculation toward the end of today's class. Then this line here that touches the curve once, locally I mean, is called a tangent. And finding the slope of the tangent is a difficult calculation to do, or I would say maybe it's an annoying calculation to do if you don't have calculus at your disposal. So in order to discuss this here, I'm going to do this in the last bit of today's class, the last half hour. But this one over here, this slope of a tangent, is the fundamental blueprint, if you want, for calculus. In order for us to even discuss this type of thing, we first need to talk about a mathematical tool or an operation called a limit. So we're going to talk about things called limits for a large portion of today's class. And then after that, I'll come back to this idea of slope of a tangent and slope of a secant through a series of examples. I don't think that you're going to find today's class exceptionally difficult in terms of algebra, but you will find it possibly a little bit challenging in the beginning with the limits. I promise you though, as we do more and more limits, it gets easier and easier. So that's my intro, and we can begin now. So we're going to move on, and today we're going to cover, for those that are wondering, we're going to go up to question number 29. And then you'll have your quiz. The quiz is going to be at 11:20 as per last week. And it's based on last week's material. So we're going to talk about limits, and we'll just see how that goes. So limits are a very interesting little thing to learn here in math. So let's go to example 1. If you don't have the book downloaded, I'm sorry I had to post it this morning as your classmates had requested for me to upload it. But anyway, you can focus on the picture here, and then perhaps you can get the video of the lesson on Friday, or the pre-recording today after class, and then you can go through the booklet again, because there's nothing wrong with going through this thing twice. So what do we have here? It's a little bit cumbersome, and this picture here represents some function. I don't want you to worry about what the equation of this function is. And I also don't want you to worry that, oh, when we do this question, maybe some of it you have gaps and you don't understand. Because this question, as you see it, we're going to do 3 or 4 additional ones just like it. So through repetition, you're going to be fine. In fact, in my past years of teaching this, usually half the class gets the first one, and then half the remaining class gets one. And by the 4th iteration, pretty much everybody has it. And at that point, I can go individually and sort out details. So what's going on here? Well, if you look at the bottom of this page here, I'm gonna just give you the picture. All you need really is the picture and this table. So if you look here, you'll see it says lim. Let me use my stylus actually. You see it says lim, and then it says x arrow -2 minus. And then f of x represents this function. This is f of x. So what this is saying is, it's saying that as x approaches, the arrow means approaches, as x approaches -2 from the left. So where's -2 on the graph here? Here's -2. I want you to pretend that you're like a little insect walking along the graph. So if this is -2, maybe you're somewhere here. And as you approach x equals -2, the minus here means from the left. To what y value does it look like you're approaching? What y value does it look like you're heading toward as you're traveling along the curve? Like if you were walking along the curve like a little insect, yeah, you're approaching, it looks like you're approaching a y value of 2. Maybe at 2 there's nothing. Maybe at 2 it's a cliff. See, it's a cliff and you fall down. It doesn't matter. All I care about is just before you get there. And yes, Anthony, the answer is 2. Very good. Now, that's called a left-sided limit because we approached it. The negative sign here means from the left. Now, this is the same blueprint, but here it says a plus sign. So what does the plus sign mean? It means as you approach from the right. So here's -2, and here's the curve from the right. Let's say that you're starting over here and you're walking along like a little insect. To what y value does it appear that you are approaching? As you go along the curve, to what y value do you think you're heading toward? The answer is -1. Remember, -2 here is the x value, but the y value is this thing. The limit, just so you know, a limit always equals, in this case, all of these pictures will be a y value. Because we're just asking you to what y value are you approaching? Because this thing here is really just y. All I'm asking you is what is the y value as you get closer and closer? Okay, this one here is interesting because you notice that here it doesn't have a plus or a minus sign. So whenever you have a limit x approaching some number and there's no plus or minus, it's understood that you mean both the left and the right. So in other words, if you take these two things here and you unify them, you consolidate that into one limit. So when you don't have anything here, which is what you're always going to get pretty much, this is what you're going to see in the future, these guys. You're not going to see these guys in the future, for the most part. Anyway, if you do that here, well, wait a second, these don't match. So the overall limit, you would write DNE. What do you think DNE stands for with math, when we're talking about math? Thank you, Prabidi. Does not exist. This limit does not exist. In order for the limit at some value of x, whatever it is, in order for that limit to exist, both the left and the right limits have to approach the same value. Let's try here the next one. So we have 0 and then 0, okay? 0 from the left and 0 from the right. So I'm going to do this one in a different color so that you can study these later. Let's use pink. 0 from the left and 0 from the right. Here's 0. And here's, as you go from the left, what is the y value approaching? To what y value do you think you're heading toward? Thank you, Jai. And what about from the right? Thank you, Anthony. So I'm happy for your participation. I really want people in the chat too. I don't know if the people that are commenting have taken calculus or not before, and I'm not asking you to tell me that, but if you haven't taken calculus, you're my target audience primarily for this first hour today, okay? Because the people who have taken it, they've seen this before, and it's kind of like a review. Anyway, this is the overall limit at 0 as x approaches 0. So may I ask here, do the left and right limits approach the same thing? Do they both approach the same number? Are these numbers the same? Yes. So over here we put a 1. So when the left limit and the right limit are equal, that's good news, because then the overall limit is just whatever individually they were. Actually, a neat little comment here. Can you tell me, what do you think of the graph here? Is the graph doing anything weird here? Or is it just a regular graph without any breaks to it? Is it jumping around? Does it jump? Does it have a hole? Does it have any weird stuff happening here? No. So if the graph is simply just doing its thing and there's no breaks or discontinuities, we say, then simply whatever the y value is, in this case 1, is what the limit is. So that's the easiest possible scenario. Let's talk about x approaching 3. So here's 3. So let's talk about as x approaches 3 from the left. So as x approaches 3 from the left, that's this one here, to what y value does it look like you're heading toward? Toward what y value are you approaching? So the answer is 0. So Shaq, you just gotta think about this, okay? You're going down the curve, and you're asking yourself as you get closer and closer to 3, so what height, what's the height here? What's the height approaching? It looks like you're getting closer and closer to 0. The actual value is this, but we don't care about this. We don't care about the actual y value. We don't care about where the solid dot is. All we care about is the trend, okay? Limits are all about a trend. So the trend here from the right is also that you're trending toward 0. And since those are the same, the overall limit is as well 0. And there you have it. There's your first example for today. And we're going to do this over and over again a few more times until you get a bit more confident, and hopefully that makes more sense. So here's another graph. This time we're going to investigate the limit from 4 different locations of x. So here's the first one, which is -4. So -4 is here. And from the left, to what y value are you approaching? What does the y value trend toward? Yeah, it's a 3. And from the right, if you look here, it's trending toward what value? What's the y value approaching? Very good. Very good. And here's a rhetorical question. Are these the same? No. So what do you put here if they're not the same? Thank you. You put DNE, which means does not exist. Awesome work, people. Okay, now -1. -1 is the easiest question because it's just a regular point. The left and the right, there's no weird behavior. It's not jumping like this one over here. So this is 4s across the board. From the left and from the right, they're both approaching 4. So overall is a 4 as well. Here's x equals 2. So that's the next one here. You see x equals 2. So as you approach 2 from the minus, which means from the left, to what y value are you approaching? -1. And from the right, here's from the right, if there's 2. From the right, you're approaching a value of 5. Okay, are those numbers the same? No. D and E. If anybody feels comfortable at this point, maybe in the chat, tell me if you have not taken calculus before. Who has not taken calculus before? So what do you think, guys? Anthony, Michael, wow, you have not taken calculus. Beautiful. Beautiful. So what do you think so far? All of these naysayers. What do you think so far of this limit stuff? Is it okay? What do you think? Why isn't the highest point for x 5 something?
For the middle right side, um, you referred to like when you went to like if you look at the middle x and the next one to the left.
Just you have to tell me on the grid here what value of x.
Oh, sorry, -1, 4.
Okay, yeah, this one here.
Isn't the arc though of the parabola higher though, or
Oh,
are you just looking for the intercept?
we're not looking for, all we're interested here is this, what value of x are we investigating? It's -1.
Oh, okay, so you're just looking for that intercept.
So this value here is the location. We're not talking about intercepts. We're not talking about vertex or anything like that. Okay,
Sorry.
so like it's okay. So over here, if we take a look at this one, see it says x approaches 4.
Yeah.
X approaches 4, then you have to cite yourself to this area here. That's 4, right?
Mm-hmm.
You have to have tunnel vision. Tunnel vision.
So
No,
basically,
no,
for the x, so the y's that has to be given. You're not following the parabola.
no,
It's
no, you're
asking you
not.
for the point.
You're following the behavior of the curve near x equals 4.
Okay, I think I get it. Thanks.
No problem. And there is no jump scare coming, Anthony, so don't worry. It just turned, actually, the algebra stuff's easier than the graphs. The graph part's the harder one. So over here, we have x approaches 4. So here's 4. If we come from the left, it looks like we're approaching what y value from the left? To what y value would you approach? That's good. Thank you, Anthony and Jordan. Okay. And from the right, you approach a y value of 2 as well. So they're all the same. I really want to bring to your attention this one. You see how this one's filled in, but this one's a hole? The idea of a limit, I don't care if it's filled in or not. Did the fact that the one here that I've highlighted here in the left, that it was a solid point, that it was filled or included the value, does it matter that it was open or closed? Did it affect the method? No. You still got the same stuff. You got the same number all across. So you don't care if it is a hole or not. The hole is not the issue. The place where limits break down are jumps. Jumps are where limits fail, and other places if perhaps the function doesn't even exist at all. Those are pretty much the two ways that limits fail. We also have things with vertical asymptotes, but those things are not going to be of a big concern to us in this course. So here's another graph. Just mention here that this is a vertical asymptote, so this goes up forever. So I'm going to do -1 first. So here's -1. So to repeat the answer, limits fail when you have a jump, but where like this type of jump here, that's guaranteed failure. And there's other scenarios which I don't have pictures to show you, but for now, if you have a jump like this, the limit fails, okay? You're welcome. So let's take -1 to start because it is the weird one. And then the other ones are pretty much routine like the other ones we just did. So when you look at -1 from the left, it actually shoots up forever. And the way that you put forever is you put this symbol here. What does that symbol represent? Infinity and beyond. Yes, Buzz Lightyear. Thank you, Jai. So it's infinity. And from the right, it also shoots up to infinity. We actually call it positive infinity because if it went down like this, it would be negative infinity. And I don't have to write the plus sign because it's unnecessary. So because they're all the same, because these are the same, then you can just put infinity over here too. And that's fine. Now the ones that I left over are actually not too bad. The only thing that's a little bit annoying here is that the y value, it's hard to read the y values here. So you'll notice that I put these squiggly approximate equal signs. because even myself, I'm not confident about what the actual number is. So yeah, don't sweat that too much. So I'm just going to put down some estimates. So if that's okay, just bear with me. If your estimate's off a bit, it doesn't matter, because if I ask you a question like this on a test, I'll use much nicer numbers. Anyway, over here from the left, so here's -3. Here's -3. From the left, it looks like it's I put negative point in my notes. Now, yeah, if you see Anthony put -0.7, we're not going to debate that too much, if you don't mind, Anthony. So your answer's right and my answer's right. And then the other one from the right is like up here somewhere, which looks like it's 0.7. So the conclusion is that we don't have a limit that exists. Let's take another one here. So this one's an easy one. This one, I'll put a happy face here. Well, that's supposed to be a happy face, but my marker went off. Anyway, it's a happy face because you see the graph? It doesn't do anything out of the ordinary. You just read the y value. So the y value here is just 0. So when the graph is just easy, that you can just read the y value, like it doesn't jump or do anything of a discontinuity in nature, then you just read the y value. Finally, we have x equals 2, which is here. So from the left and from the right, it seems to be trending toward -0.5. Now, the actual y value is this, but I don't care about that point. It's not, I don't throw it away. I'm just saying I don't care about it for the limit. And there you go. That's just another question with limits. Now, I'm picking up the pace a little bit. I went very slow on the first one, but you can see here that the process starts to accelerate because you're getting hopefully more proficient at it. This one here, sometimes you'll get pictures where the values don't really match the grid well. So we'll see this one here. It says -2, 1, but it's not at 1. Don't worry about it. I ripped this picture off of somewhere, and obviously I think it was a Google free images, and it was obviously, that's why it's a free image, because it was broken. Anyway, when you want to evaluate these limits, I really want you to have tunnel vision. So this is what I mean here. Like take a look here. See that? That's the analysis for this one. Think of it as tunnel vision. And then this one over here is for 1. So here's 1, etc. I'll do one more in pretty color, and then we'll just do the math. So here's 2. So you're just looking kind of here all the way up. So that's how you analyze it efficiently. So for example here, -2 from the left and the right is approaching a 1. So 1's across the board. And then over here, 1, again, from the left and from the right, it's approaching 2. So nothing strange happening there. The limit exists. This one is the funny one. That's the messed up one. So let's talk about this one slowly. 2, here's 2. From the left is right here. And that's a y value of 1. But 2 from the right is up here, which is 3. Hence, we have a limit that does not exist at that location. And I ran out of colors, and I don't want to use my... I could add another pen here, but you know what? It's too early in the morning for that. So we'll just do this one without any special features. I'm going to go over here and put that from the left. So here's 3, of course. There's 3. From the left, it approaches a y value of 2. And from the right, it approaches a y value of 0. So it does not exist also. So what we've done here in this first 25 minutes or so is explored what are called graphical limits. So if we go back to the outline here, what have we covered right now? Now don't get too intimidated, because it looks like we're not progressing very much, but we just did this one, just that. Which question, Max?
The previous one.
This one here?
Yeah. For the left side, limit x to the 1.
Yeah, from the left side?
Yeah, because isn't one of the x's negative?
Okay,
Like,
this is x equals 1, right?
uh,
And this is the left side of 1.
but aren't you trying to show where it's going?
It's going towards 2.
Okay.
It's going toward a y value of 2. The left side and the right side refers to the graph itself, Jordan. So, like, if you pick -2 here for x, then nearby -2, if you look in this window here, as you approach -2 from the left and from the right, the y value tends toward -1, tends toward 1. Because if you think of it like a number line, this is -2. This is -2 here. Where is left of -2? It's over here. So as you come up from this way, what is the y value heading toward? That's what you're asking. So what we've covered up to this point is what's called graphical limits. Now we're going to move on to something called algebraic limits and limits with tables. Because as you can see here, the graphical limit is a little bit irritating because there's no formula attached to it. I really want to say that this graphical limit exercise, even if it doesn't, even if you're one of the people that might not fully understand how it goes yet, it's not the only way to visualize limits. Because instead of using a picture, if you had a formula for this graph, which we don't have for this one, you could use a table. And that's what we're going to do right now. So take a look at this function here. So imagine I plotted it. I could plot this. I'll plot it at the end. I'll put a graph of it right here at the very end. But for now, I just want you to simulate, doing this limit. See, x approaches 1 from the left. So if you were on a number line and you were approaching x, if you were heading toward 1 from the left, if you think of a number line here, here's 1. Here's left of 1. How about 0.9? That's pretty close, and that's what you have here. But you know what's closer than 0.9? 0.99. And you know what's even closer than that? 0.999. So what you're doing here is you're simulating traveling along the graph without actually traveling on the graph, instead just using a table of values. So I'd like you to grab your calculator and plug in 0.9 into this function. Now, it's a little bit of a chore because there's lots of them, but convince yourself that you can get at least the first answer. So I'm going to give you some time here. I'd like you to get the number in this box here. So give me the value for x when the value for y when x equals 0.9. Just type your answer in the chat once you have it. Thank you, Irvin. So I'm going to give everybody here 2 minutes. I want you to get 1.9. Hit me up in the chat when you get it. Just type 1.9 in the chat when you get it. Once I what part of it, Shaquille? This is x, and I want you to find y. This is y. So if you plug in 0.9 into here, what do you get? You should get 1.9. Thank you, Prabiti. Now my computer's freezing up a bit, so I might cross my fingers here. Put 0.99, you're gonna get 1.99, and if you put 0.999, you're going to get 1.999. So there you have it. As you start putting values of x that get closer and closer to 1, you see how these numbers are getting closer to 1? It's just like traveling along the graph from the left. So as you travel along the graph from the left, you're getting closer and closer. What is the trend here? Tell me the trend. What is the trend? What are these numbers getting closer and closer to? Thank you. They're getting closer and closer to 2. See? As you get closer and closer to 1 here, then these values are getting closer and closer to 2. Chase, you can do the numerator and the denominator separately then, okay? Probably your safest bet. If you're not getting it, otherwise you have to put brackets and then you divide with brackets like that. So make sure you put lots of brackets, okay? But yeah, just for starters though, just type them separately. So as you travel along this curve, you actually get closer and closer to 2. If you've succeeded with these calculations, you can go over here and try the same thing with 1.1. So if you put 1.1 in here, it's like you're over here now. Let's say that you're at 1.1, and then you would get something. And then if you put 1.01, you're over here, and then 1.001, you're over here. So your target is to get to 1, and you're simulating traveling along the curve and slowly but surely getting closer and closer to the true y value. If you put 1.1 into this function and you get the y value, put 1.1 into there, you get 2.1. And if you put 1.01, you get 2.01. And if you put 1.001, you get 2.001. It's not always this obvious or nice, but you can see here that as these numbers get closer and closer to 1 from the right, then from the right on a number line, if you like, that's what we mean from the right. It means along the number line. Then these numbers get closer and closer to what? What is the trend here? Thank you, Vittorio. It's getting closer and closer to 2. And there you go. So that is the left and right limits using a table of values. I didn't use a picture this time. I used the table of values. So are these numbers the same? Yeah, they're the same. So then the overall limit is 2. So if you go to the previous example, what we just did in this question was did one of these rows. We filled in a row without actually having the picture. That was the purpose of this table, was to travel through that process. So what does the graph look like? Because I said I'd give you the graph. The graph looks like this. You don't have to know how to graph this one, but if you've taken advanced functions, you should know how to graph it. The graph looks like that. That's the graph, people. You see how there's a hole at 1, but it doesn't matter because the trend, as you go from the left or you go from the right, it doesn't matter because the answer is 2. So anyway, I hope that was a good experience so far. The process can be repeated for the next one. But for this one here, I might leave this one as just homework, okay? Or I'll probably do this one during the break, okay? Because I need to focus on on some algebraic limits. So when we have a break, I will go and silently fill out this table, and you're welcome to follow along with me, or you can try it later on your own. But the idea is that you're going to simulate traveling along this graph near x equals 0, because the limit is near x equals 0 for this situation. And we'll go through that process during the break. I'll just point out that the answer is going to be 1, 1, and 1. But we will definitely go through that during the break as an optional extra question. The E scares you. No, we did E last time. We did E in class already. We're not going to, guys, we're not going to do anything too dangerous here. For BD, this is just something I want you to plug in. If you plug in if you plug in negative 0.1, can you plug in negative 0.1 in here? Yeah, that's all I'm asking you to do. That's all I'm asking you to do, people, is plug negative 0.1 in here for x. That's it. Yeah, exactly. Thank you, Shaquille. It's just that. It's not as bad as you think. If you want, let's do the first number, and then you can come back to it during the break. We'll come back during the break. Yeah, it's the inverse of ln. Anyway, we'll come back to this during the break, okay, people? Just see that the numbers are getting closer and closer to 1. So it's just plugging in numbers. All you've done so far is read a graph and plug in numbers. I'm still not getting near those numbers. What do you mean, plugging in this? Getting this first number here, Chase? Okay, you have to type in e to the negative 0.1. And for this question? I don't understand, man. Like, take this first one here. 1.9 squared minus 1. And then type in 1.9 minus 1. And then divide the two. That's all I'm asking you to do. That's all I'm asking you to do here. And for this one here, the same thing. For this first calculation, e to the negative 0.1 minus 1. And then the denominator is negative 0.1. And divide the two answers. This is not an issue of calculus. This is just calculator work. If we go back to our list here, we've completed limits from a table of values. And really, the heart of today's lesson is this one. So the first two things that we looked at were more about visualizing a graph and visualizing a limit on a graph. But what if you had to do an algebraic limit? So now these questions here are basically taking the stuff we did on the previous pages, saying, look, I don't need a picture, I don't need a table of values. Can I just plug this in? This is your function here. This is f of x. That's your function. And this is just saying the limit as x approaches 3 of this function. The way that you do these kinds of limits is you just try to plug in the number. And if you can't plug in the number, then you have to do some extra work. So for this question here, I ask you, can you just plug in the number here? Can you plug the number in there? What happens if you plug in 3 there? What do you get? Yeah. If you can plug in the number, that's just the answer, okay? That's all you do. Nothing dangerous, nothing strange, nothing scary. That's it. For example 8, again, can you just plug in the number? Yeah, you can. Absolutely, you can just plug the number in. And because you can plug in the number, then finding these limits is pretty easy. So here I just plugged in 3, just like Anthony did. So I put in 3 for x everywhere, and it's just reading the y value. The analogy is that the graph doesn't have any strange behavior here. It doesn't have a jump or a hole or anything strange. So you don't have to worry about any behavior that's out of the ordinary. Okay, so those types of limits are supposed to be super, super easy, and almost as easy, I would say, as the graph here. This one here. See this one here? There's no strange business happening here, no strange behavior. So this one here, you would just read the y value. So the y value is 1. So that's why you just put 1, 1, 1. And that question over here with the algebra is the same type of question. If you were to graph this, the graph does not exhibit any holes or jumps or any asymptote, nothing crazy. It's just literally a very predictable graph with no discontinuities, so you can just plug in the number. In contrast, though, the following limit is a problem. Take a look here. If you plug in 4 here, what do you get on top? What do you get when you plug in 4 on the top? And what do you get when you plug it in on the bottom? So we get a situation where it's 0 over 0. Now the thing with math is that 0 over 0 is very strange. Very good, Vittorio. It's a hole. It is a hole. That's correct. I'm going to mention this word 0 over 0 a lot in this course. 0 over 0, you know how people write undefined? It's not undefined. Undefined means it doesn't work. You don't know what it is. Indeterminate, undefined means does not exist. Indeterminate is what we have here. Indeterminate means I don't know. I don't know what's going to happen. So whenever you get 0 over 0, which is the majority of the ones I want to do with you because they're related to the calculus formulas, whenever you have indeterminate, you need to do extra work. So I have to copy and paste this for the sake of time. But what I did here was I used some algebra. So over here, you see what I did? I factored the numerator. I factored out that numerator, and I got x minus 3, x minus 4. So that's what I was telling you back in September, that you need to know factoring for calculus, which is why I even covered it. But you notice that these x minus 4s cancel. And now you have just this question, and that question is easy. So if you have this easy question here, you plug in 4, now it's no problem. 4 minus 3 is 1. So that's how you do these questions where you get a 0 over 0 when you plug it in. So we'll try a few more of these, and then we'll take a break. And I'll go back and do that table question during the break. So how about this one here? If you plug in 1 for x, if you put 1 on the top, what do you get? What's 1 squared minus 1? And what do you get on the bottom? So again, you have a situation where it's indeterminate. So that means that you need to factor. So the top here, when you factor it, when you factor the numerator, it's a difference of squares. See, we have x squared minus 1 is x plus 1 times x minus 1. You were very good at factoring on your midterm. And then over here, these x minus 1s cancel. So you just get x plus 1, which is a very easy question. Because now you can just plug 1 in and get a 2. So that's how you deal with limits where the situation is 0 over 0. We'll take a break now and come back to do more of these. And at this point, I will go back and just silently fill out that table and leave it for your processing. So it's 9:51. Let's resume class at 10 o'clock, okay? In the answer, would we have to state that there is a 0 at 1? No, you don't have to state that there's a 0, no. This thing on the side here, Vittorio, is just me telling you individually. The quiz from last week, I will make it available right now, Shaquille. I had marked it, but I hadn't posted the grades yet. I haven't posted the grades to Blackboard, but they are marked. So let me just make it visible to you guys. So we're gonna keep on going here now with some additional limits. Nice, Chase. I like when the calculator cooperates. So here's example 11. So when you try to plug in 3 here, what happens? If you plug in 3 on the top, let's do that just mental math. So we have 2, 3 squared is 9. So you get 2 times 9 is 18. So you get 18 minus 18 is 0. So the top is 0. And if you plug in 3 on the bottom, you're going to get 9 minus 12 plus 3, which is 0. So again, you have this, you have this indeterminate form. So that means that you need to use some algebra to fix it. So this one here is a few factoring steps, unfortunately. So when you toss in a little bit of algebra here, you get the following. So I'll walk you through the idea here. I took out a common factor of 2, and then I noticed that x squared minus 9 is a difference of squares, just like the previous question. See, x plus 3, x minus 3. And then we can remove the hole. As mentioned earlier, there is a hole in this graph, as there was with the other one. So the x minus 3's cancel, and that removes the problem. That's the x minus 3's are the factors here that are triggering the 0 over 0 result. Now that you have that, there is no issue plugging in 3. If you plug in 3, you're going to get a value of 6 eventually. So your performance on doing evaluating limits really depends on your aptitude for factoring. So if your factoring is a little weak here, it's going to be a problem. But you know what? The good news is, people, let's say this question here. See this question here? If you're like, I can't do this question because my factoring is not that good, then what happens is you could do it this way. So now do you want to use a table? I don't want to use a table. It takes forever. So that's why if you build your factoring, you don't have to use a table or even go and use software to draw a picture. Because even for this question, I don't want to draw this picture. I don't want to go to Desmos or whatever, my graphing calculator. I don't want to make a table. So that's why it's important that you understand some factoring so that it becomes easy to process. So the next question here is also an indeterminate question, as well as the question after that. I'm kind of spoiling the mystery here, a little surprise here. These two questions are also indeterminate. So if you plug in 0 for x, you get 0 on the top, and you get 0 on the bottom. So that's why it's 0 over 0. So then what you can do is, you can take an x out. So if you take an x out, then you remove the problem. See how I took an x out of the top here? I took an x out of the top, and I can cancel it with the one at the bottom, leaving me with just something that I can plug 0 into. Plugging 0 into this one here is easy. You just get 1. you might be noticing I keep on writing limit. See, I keep on writing limit here? I need to keep on writing limit until I actually evaluate the limit, which means to actually, in a way, plug in that x. So until you plug in that x equals 0, and you're allowed to, because here you can't. Here you can't, because you get 0 over 0. But eventually you can. Over here you can. So that's when you stop writing the limit. You actually write the numerical value that it produces. So factoring is the way to go for most questions, at least the ones you've seen so far, where you have 0 over 0. In question number 13, the difference is that instead of having an x, we have the letter h. So we don't have a variable x. And it doesn't matter what the variable is here. All that matters is that you are evaluating a trend or determining the trend as that variable approaches a half. So if you want, you could change all these x's, all of these h's here, you could turn them into x's. But whatever you do, you're going to get 0 over 0. And since you get 0 over 0, you need to explore some factoring. And I'll do the factoring here. I'm just going to paste the factoring. I hope you don't mind me pasting this factoring step. It's really slow to write that in. So you notice here that we have 2h minus 1 by 2h minus 1. So if we cross one of them out, then we remove the issue. And now this is easy to do. You can plug in a half in there. And if you plug in a half, you get 2 times a half, which is 1, minus 1, which is 0. So you get 0. So those 5 or 6 questions that I just did that were 0 over 0, they play a central role. They are essential to us discussing calculus. Out of all the stuff that I've shown you in the first hour and a bit of today's class, these questions here are the most critical for you to understand. In terms of the next few questions, these are just more of a novelty. Nothing here to really discuss out of the ordinary, at least for the next two. For this one here, can you plug in -3 here? Do you see an issue plugging -3 here? I don't see an issue. Just plug in -3. And don't worry about calculator work here. I didn't even use my calculator. I just literally just like plugged it in. So you see there, I just plugged in -3 and then -3 for x over here, and I added 3 at the end. Of course, these numbers here at the end here, this here equals 12. And then that one there, you make sure that you write it with a positive exponent. So if you can plug in the number, go ahead and do that. Including the next question. The next question, you can also just plug in the number. There's no problem plugging in a 6 there for x. If you plug in a 6, you're going to get log, where'd it go? I lost my screenshot. If you plug in 6 there, you just get 3, because it's 6 minus 3. So the answer is just log of 3. And that's pretty much it. This last one here is just, the last one on this page, I mean, is just going to be plugging in 1. And this one here is interesting because if you plug in 1 here, it means that you're taking a log of a negative. This is not an issue with limits. This is an issue with the function itself, because you cannot take a log of a negative. As mentioned last week, one of the features of the graph of logarithms is that if you take a log of a negative, it does not exist because the domain, it's outside of the domain. You can only take a log of a positive number. I don't care what the base is. In this case, it's base 10, but whatever base it is, you can only take a log of a positive number. I realize that I'm really slamming you with algebra today. but it was forewarned. It was forewarned that you need algebra. For this example here, is there any problem plugging in -2? Not really. There's no fractions. If there's no fraction, it's not going to be 0 over 0. Yeah, for logs, don't do anything else. Don't touch your calculator for this stuff. All we're doing is experimenting with plugging in numbers, Praviti. That's all. You're welcome. Those last two questions with logarithms are more of talking about the failure of limits, or the fact that the limit does not exist, not because of limits themselves. It's because the function doesn't exist. If the function doesn't exist, how could you expect it to analyze a trend for it? So that's the purpose of that question. Those two questions. This last one here is just kind of like, you know when you do like a workout at the gym and then you finish the workout? This is cool down. We're doing the cool down now. You just, another easy one just to finish off, plug in -2. Kind of finish how we started, right? So if you're able to just plug the number in, remember, if you can just plug the number in like I did here, I got 51, then just do that. No problem. So that's enough about limits for a little while. I told you that you need to know limits to understand calculus, but I'm not going to mention the word limit in terms of actually doing questions with you now. But we will use the idea or the operation of a limit in next class. So next class, you're going to see limits for the first hour, most likely at most the first hour. And then for the rest of this course, you will not see limits again. And that's it, okay? Just putting it out there for you. So what we're going to do now is going to go back to what I said at the beginning of today's class. We're going to talk about slope of tangent and slope of secant and slopes and rate of change. So I'm going to take you back now to grade 9. And I want you to find the slope between these 2 points. Who remembers how to find the slope between 2 points in a graph? This is grade 10. No, grade 9. It's grade 9. Who remembers that from grade 9? How do you do that? What's the formula look like? Anybody remember the formula for slope? Have I scared everybody off? Thank you, Jai. Thank you, Jordan. Thank you. That's the one. This puppy right here. Remember this one back in the day? Slope. y2 minus y1, x2 minus x1. Yeah, just do that. So plug in those points and get the slope. Hopefully it doesn't take you more than a minute. Yeah, the first one, that's right, Anthony. The answer is 6. I'm going to put the calculation on the screen in a second. So if you put there 6, there you go. And for the second one, obviously I'm not trying to chase anybody here, but hopefully you don't have too much stress. It's close, Anthony. It's positive, I think. I think it's negative, the answer. Yeah. Talk to me. Talk to me in the chat, people. What do you think of this slope stuff? Who remembers this stuff? Who remembers doing the slope stuff? Easy. Thank you, Irvin. Max, what's going on? Okay. So I think we're just gonna not talk too much about this type of slope because it's the slope that you know from, well, I guess now 5 years of your life, probably, at least. Now, let's talk about how the slope can be found for what's called a secant. So this is the equation for slope when you have 2 points, and you don't need a graph. I don't need a graph here. This situation is that a grid, and I have 2 points on it. By the way, this diagram is not to scale, so don't worry too much about how I've drawn it, okay? Obviously, I'm not doing a good job drawing this, but There's 2 points. There's no function. There's no f of x. There's no curve. There's no graph, okay? It's just 2 points. But in the next question, I'm asking you to find the slope of a secant. Now, secant is different. Secant is that you have a curve. So in this case, the curve is the parabola. This is y equals x squared. See, here's your parabola. Like that. And I'm asking for the slope of the secant. So a secant is a curve that touches this, is a line, a straight line that touches the graph twice. So maybe from here to here. See that? See how that green line segment, it touches the graph twice? That is a secant. So I'm asking for the slope of that secant. This is x equals 3, and that's x equals 4. And then you can find the y values and draw a triangle. So that's what I'm asking you to do, without drawing the triangle, though. So the formula for that is going to be this. So instead of writing y2 minus y1, we write f of x2 minus f of x1, okay? That means the same thing. So f of x2 is a more mature way of saying y2, because we're using function notation. So what is f of x2? Well, it doesn't matter which one is which here, but let's call this one x2, and let's call this x1. Just because it doesn't matter which way you call it, but I call it that way. Then in this case, that would mean the following. You get the following value. See, you plug in 4 into the function, so f of 4 means that you plug in 4 into f of x. So where the x is here, you plug in a 4, and f of 3 is that you plug in 3 wherever the x is here, so you get 3 squared. And then, of course, x2 minus x1, that's like the old slope stuff here. It's just the 2 x's subtracted, so 4 minus 3 is 1. And eventually you simplify this and you get a 7. So a footnote to this is that the slope that you just calculated, that represents what's called the average rate of change. Average rate of change is often called AROC. Who's heard of AROC before from maybe a teacher in high school, a math teacher? Yeah. Anybody else heard of AROC? AROC? In calculus? Nope. Okay, so what does that say? So if you have this graph here, what it's telling you is that from here to here, the graph is changing a certain amount for a given change in x. The best way to say it is, I want to write it better here. I'm going to just type it out in a sentence here because it's easier for me to say it. I'll just write it out here. And I'll shrink the font in a second. From x equals 3, okay, from x equals 3 to x equals 4, on average, the graph is changing at a rate of 7. That's what the statement that you just calculated says. It says, on average, from x equals 3 to x equals 4, the graph is changing. If you want changing, you can say it's growing at a rate of 7. It's growing at a rate of 7. Why 7? Because if you draw a triangle here, let me draw a triangle here. The slope is 7 to 1. 7 to 1. So I'm going to ask you to do some more slope of secants, and it's just extra practice. But before I do that with you, I want to take you back to the cover slide and remind you what we're trying to do here. So right now, I'm asking you to calculate the slope of a secant And the purpose is that if I wanted to find, ultimately I want to find this one, the slope of the tangent. If I take this second point and I get it closer and closer and closer and closer, if I get that point really close, like right here, then that slope there will be closer to the true tangent slope. That's the idea, what we're trying to do in this next series of examples. So in this case, instead of finding the average rate of change or the slope of the secant from x equals 3 to x equals 4, what if we went from 3 to 3.1? So you see how 3.1 is closer to 3. We're actually finding the rate of change on a smaller interval. So let's find that slope of the secant there. Yeah, it's 6.1. That's good work, Anthony. I'm gonna give some people time to do that here. So what you want to do is, in this case, f of 3.1, you're plugging 3.1 into the original function right here. So that's 3.1 squared. You're close, Jordan. It's 0.61 divided by 0.1. And then if you put f of 3, yeah, that's better. So that's equal to 3 squared. And then the bottom is easy. The bottom is just 0.1. So if you simplify that, you're going to get 6.1. That's good work. So what I've done there is I've asked you to put in, to find the rate of change on a smaller interval. So if I took the previous graph and I narrowed it, what we've done here is instead of using 4, we use 3.1. And I brought those points closer. So this is the tangent, which is our goal, down here. And you see how these are very close to each other now. It's 6.1. We can repeat this process and do it even closer with 3.1, 3 and 3.01, or 3 and 3.001. And you'll have a continuing trend there. So if you plug in 3.01, if you plug in 3.01 into this process, you're going to get 6.01. So the key step is right here. The one that I drew in color on the previous example. And if you plug in 3.001 for the second point, you'll get even closer. But regardless of what you do, you start to see a trend emerging. See over here we have an answer that gets closer and closer to 6. So if we summarize this together, you can actually figure out, or at least predict, I should say, based on a trend, what the slope of the tangent will be. So what I want you to do is in the next question here, I want you to just think about what the actual slope will be overall. All right. So how do we do the actual trend here? So can anybody suggest to what value does the slope approach? What is the value that the slope is getting closer and closer to? Thank you, Lucas. It's getting closer and closer to 6. I'll actually summarize it with a table. I made a table here to make it easier. So let me just pop that up here. See, what we want is the slope of the tangent. We want the slope of the tangent at x equals 3. But it's impossible to find the slope of the tangent when you only have one point. So that's why you need to use 2 points. So you see here that when you use 2 points that are really, really, really close to each other, so if you have that graph there, and this is x equals 3, here's x equals 3, you want this slope here, this tangent, like that. What you did was, what we started with was a point over here. Let me draw the points in pink. So you started with a point over here like this. And that pink slope, maybe it was this one. You see, it's okay. It's not that bad. But let's try a better guess. So we do the orange one, which is, let's say, over here. Now, the orange slope is looking a little bit better. That's this one. And then you go to the green one, which is really, really, really close. And they're very, very close. So that means it's even a better estimate. So that's the idea of what we were doing here. We were calculating that tangent slope by finding out what the trend is. So when you ask for f of x equals x squared at something, you pick a number that is close to itself. Basically, yes. Yes. The good news is, Anthony, that you don't have to do the stuff I'm showing you here. Is more of an experiment, more of a process for you to understand better how to do things. But in the next example, I will give a formula that you can use to estimate the instantaneous rate of change. So example 25 is your opportunity to actually use a formula to find the instantaneous rate of change, to make an estimate. And it goes like this. It's this formula here. So I'm just going to put the formula here, okay? So that is how you do an estimate for the instantaneous rate of change. And I'll explain what these quantities are in a second. So in this case, we're given the values here, and we just apply them to this formula. I want to emphasize here, it is an estimate. It's an estimate. So see this here is h is 0.001. If you wanted to have the exact value would be h equals 0. But we're going to get to that in an example or two from now. So for this example, we can evaluate, or estimate, I should say, the instantaneous rate of change. I haven't gotten that far yet, but I will get there closely. So in this case, the instantaneous rate of change is going to equal, if you plug in the numbers here for x and h, you get f of 2.6 plus 0.001 minus f of 2.6 over 0.001. And I'll go through that very slow here. It's totally cool. So that equals f of 2.601 minus f of 2.6 over 0.001. So the function here is the parabola. It's x squared. You see the formula is x squared. So that will equal 2.601 squared minus 2.6 squared over 0.001. 0.001. So then the instantaneous rate of change is going to equal whatever you get on the top, which I got 0.005201 over 0.001, which is 5.201. So that's the instantaneous rate of change. The instantaneous rate of change is roughly 5.201. I actually am not asking 2.601. How did I get that here? This one here, Jordan? Or Shaquille, sorry? Yeah, I did this. I just put 2.6 H. So 2.6 plus H. It's all good. Okay. If you're wondering what is the exact one, the exact value, we're not doing that today. I'm not asking you to find the exact value in this example. Maybe we'll cover it toward the end of class though. I'll just say here, note, we will later see. But that's not for discussion for this example. It's just estimating the instantaneous rate of change. This is the kind of process that we can talk about now. I want to take a step back here and just say to you, I could have started today's lesson just talking about what a secant and what a tangent is, and then give you this formula. I could have done that for today's lesson, and then I could have done like 30 of these examples. But I do believe though that when we do start the actual calculus, which is next week, the actual like big formula for calculus, if I just did that with you, then you would be in a position that you don't really understand what a limit is, and you don't really understand how to use the formula. So all that stuff I did with limits earlier, I know that it might have intimidated some people, but you need to know a little bit about limits so that you can do the work that we're going to do next week. But you don't have to be experts. Let's try another one of these questions with this formula here. And we're going to get close to wrapping up the most dangerous part of the learning process. I think today's lesson is probably the hardest of the 4 lessons because it's a lot of weird things happening and you're not really sure how they fit together. But next week, they'll start to fit together better. So for this example, we're given the information in the question. So we just have to play around with it and plug in the numbers. So we're estimating the instantaneous rate of change. And in this scenario, it's 1.49 for x and that for h. So that's f of 1.49 plus and then f of 1.49 over that. And then that becomes 1.4901. Notice this time, though, we don't have a parabola. We don't have a parabola this time. You see the function here is a cubic. So you got to plug it into the appropriate places in the cubic. So when you see this cubic function here, it's going to be a bit of a mess. For the first one, you're going to plug in 1.4901. So that includes the following template. So that's the function there, a template for it, and you got to plug in those 2 numbers. So you're going to plug in 1.4901, and then you're going to plug in 1.49. And it's a very long writing process. So we're finding the instantaneous rate of change, but this time the function is this cubic function. And we're finding an estimate to the rate of change. So the estimate, we use this formula, where x is the location at which we want to know the rate of change, which is 1.49, and h is the interval on which we want to find the estimate, meaning that we're drawing a triangle that is this wide. And then you find the actual x values for the two endpoints of the interval. So the one endpoint of the interval is 1.49, and the other endpoint would be 1.49 plus this value here. If you add 0.0001 to 1.49, you end up with the following formula, the following expression that you want to evaluate. Now, what does it mean to have f of 1.4901? It means give me the y value when x equals 1.4901 for this function here. It's not x squared this time. It's this function, which is 2x cubed plus 5x plus 1. So you plug in 1.49 for x there, 1.4901, sorry. Then you take 1.49 and you want to find the y value for that. So you put 1.49 into the entire function here, and you get this. It's a lot of writing, a lot of typing on your calculator, and it's just part of the process. So eventually you'll get something like this, which approximately is 18.3. So this question really is just about experimenting using the formula for the instantaneous rate of change estimate. So that's what we just figured out. We figured out that if we wanted to draw a tangent at x equals 1.49, that tangent would have approximately a slope of 18.3. What is the exact value? This is one that I couldn't do in my head, but just because it has some decimals in it. But you will learn some skills where you will find the exact value of it soon. Okay, so what now? Well, I need to talk about this thing here a little bit further. This thing here has a name. It's called the difference quotient. So this thing here that you see, yeah, exactly, Siddharth. At this point, it's just plugging in numbers, but you are told what h is. Now, some of you might be bothered. You might be bothered about why is h 0.0001? Because if you wanted, no, it's actually, it's not more complicated. It actually becomes less complicated when you get rid of the numbers. It's kind of funny. It actually becomes less complicated when you get rid of the numbers. So this thing here becomes interesting because an estimate for the slope of the tangent, this is a very, very important statement. Can't emphasize this one enough. If you want to find the exact slope of a tangent, then you need to set h equal to 0. But there is a problem with that. If you make h equals 0, you actually get 0 over 0. We're going to go through this example now and show how we can actually estimate, or sorry, we can find the slope of the tangent. So there is a procedure for that, and I'll walk you through it. So that's the procedure, everybody. If you want to find the exact slope of the tangent, simplify this thing here, and then let h equal 0. So let's apply it to this question. So we start with this. And you plug in this, you evaluate f of x plus h, and then you evaluate f of x. So in this case, x equals 3. So you would have f of 3 plus h minus f of 3 over h. The function here is f of x equals x squared. So what you want to do is you want to plug in 3 plus h into this function here. So if you do that, you get 3 plus h squared. And then if you want f of 3, you plug in 3 into this function and get 3 squared. And your objective here is to simplify this here, this difference quotient, what we're doing, and eventually you want to set h equal to 0. So let's simplify this as best we can. So on the top here we get 3 plus h, and then 3 plus h, and on the bottom we get h. And then here we can distribute on the top, that's FOIL. So 3 times 3 is 9, 3 times h is 3h, h times 3 is 3h, and h times h is h squared, minus 9 over h. Anthony's a good question. Why don't we set h to 0 at the beginning? Try it. Shaquille, try it. I want you to make h equals 0 here. What do you get? Okay, it was a good question. I knew someone was going to interject on this one. If you make h 0 here, let's make h 0 right here, guys. What do you get? You get f of x minus f of x over, what do you get on the bottom? Oh, hey guys, what's f of x minus f of x? What's something minus itself? Oh, you get 0 over 0. You see that? You can't do it yet. Try it here. You get 0 over 0. Oh, wait a second. You get 0 over... Oh my god, guys, this sucks. Look, every time it's 0 over 0. What a disaster, right? Every single time it's 0 over 0. So you know when you get to plug it in, your goal is to destroy this h on the bottom. Once you get rid of the h on the bottom, then you can make h equals 0. So that's a very good question. That's why we don't do it right away. It's a very, very, very good question. So let me take this statement here and keep on working on it. Yes, that's right. That's right, Jai. I'm gonna finish this one up slowly though, but you are correct with that. So if we look here, the 9's cancel. So we get h squared plus 6h over h. And we're almost there, because you can take an h out. This reminds you possibly of the algebra that we were doing with limits in the first hour. But those h's cancel. Excuse me. So guess what? Once you cancel those h's, there you're good. So you see all of this stuff here. Whoops. That's all step one. That's all step one, people. And here's step two. Step two is easy. That's it. That's the answer, everybody. Yeah. Oh, shoot. That's a typo. Set h to 0. Thank you. Thank you, Jai. Keep me honest, my friend. So that is how you find the slope of the tangent. That was exciting. We're gonna do one more of these, but we're gonna take a break now. Take a break until 11 o'clock, and then we'll do one more of these, and then your quiz is at 11:20. So I'll be back here in 5 minutes or 6 minutes or so. All right, can you hear me and see me, please? Thank you. So this last thing that we're doing, this last example we just did, is the most important question that you're seeing with me today. I want to say that for 100% so you understand. What we're going to do next week is the exact same question. What you just see on the screen, 27, we're going to do the exact same question, but instead of writing it with 2 steps, we're going to take advantage of our knowledge of limits, and we're going to write a formula that has a limit instead of the 2 steps. It's more compact. What we're going to do now is do one more example. We'll do 28, and that's it for today's class. And then 29, you can try it on your own. It's 29 you won't get 29 on a test, but I'm just have it there as extra challenge for perhaps some of the people that are a little bit stronger with this stuff today. But anyway, it's extra practice regardless. So let's go to question 28 and apply the exact same strategy to estimate, no longer estimate, sorry, to find the exact slope of the tangent. So let's go through that process that we just said. Step 1. So we start off with this expression here, which is what's called the difference quotient. So let me say that here. And I'll just say it like in the background here. In other words, get rid of h on the bottom. Okay? So that's the game plan. That is our game plan, okay? So first we plug in our value of h here, which in this case is not it wasn't 3 last time. What's the value of x? Sorry, plugging in x here. What's the value of x in this example? Thank you, Anthony. Thank you, Shaquille. So you plug in that. And naturally, in this question, we have 2 terms, meaning that it's going to be more algebra to write on the paper. So I'm gonna just write that down there. And I'm going to try to color code it a little bit. So this guy over here, let's make it blue. And this one here, we'll make it red. So then this is red here. Is what happened there? Gotta love technology, right? Let's make that red there. I'll fill those correctly in a second. They're just placeholders for the actual word processing. Okay, anyway, so over here, we're going to get 2 bracket something squared minus 5 brackets. And again here, 2 brackets something squared minus 5 brackets. Where am I getting this 2, 5 brackets business? Because the function f of x is equal to 2x squared minus 5x. And instead of having x, for the first one, we substitute negative 2 plus h. So negative 2 plus h. And again here, negative 2 plus h. Whereas the other one, the value of x is negative 2. We just plug in negative 2. And if you can clean up this mess, eventually you are in good shape to finish. So let's double space this because it's looking a little bit weird. So in this first square bracket, we have 2 bracket, negative 2 plus h. And then you have h on the bottom. Now this one here, I'm going to expand that. If you expand that, you're going to get plus 10 minus 5h minus, then I'm going to put a square bracket here. In this square bracket is the numbers here in red. So if you simplify all this stuff in red, what do you get? Well, you get 8 plus 10. So just to keep you back on track here, all of this stuff here that I wrote is based on the first part in blue. And then the stuff in red later. So now we can expand and simplify this. Now this is a bit of a chore to do, but we'll do it carefully. I'm going to do this here. This is FOIL. So I'm going to do that distribution or FOIL right there first. So we get 4 minus 4h plus h squared. And then if you keep on going here, we have plus 10 minus 5h minus 18. I hope that you're not getting too scared of this. This is not anything about calculus right now. This is just cleaning up a bunch of algebra. So if you expand out that bracket, we distribute, we get an 8 minus 8h plus 2h squared plus 10 minus 5h minus 18 over h. Let's take a look here if we can cancel some stuff out. I noticed that the numbers go away. 8, well that's a 10, sorry. That's my keyboard. Me typing on the keyboard. So that's 8 and 10 and 18. So they go away. Perhaps I need to use a thinner pen there. So 8, 10, 18 go away. So now we can proceed to go on the simplify here. So we end up with, on the top, 2h squared minus 13h over h. Can someone confirm they agree with what I have? Who agrees with my statement here? Thank you, Jai. Thank you. Thank you, Jason. So I think it's good. I just scrolled over to my answer key. I try not to look at the answers for these. I try to do them myself, especially these longer ones, because it helps me establish a pace that would be fair to you. Because obviously, if I just copy and paste these ones, it's like I could copy paste in 2 seconds. Good played, Shaquille. Shaquille's on point. He is business today, this guy. Factor out that H. So that is a good play, my friend. And now that you have that, now that you have that H factored out, What did I just do there? Once you factor out that h, you can cancel it, and that's 2h minus 13, which takes us to step 2. Set h equal to 0. So the slope of tangent, slope of the tangent, which is the same as instantaneous rate of change. What's the answer? Bring it home, Shaquille. What's the answer? You got this. If you set h to 0, what do you get? Ah, Muhammad in for the win. Look at the steal. He's going in for the empty net goal. He was going in for the empty net goal, and Muhammad came out of nowhere and threw his stick for an interference penalty. Wow, faster internet wins. You guys are savages. No, he didn't choke. No, he was on point. He was on point. I'm sorry, Shaquille kicked some butt today. This is good work, my friend. Good work. Okay, so question 29 is another one like this, except the function is more complicated. It's a reciprocal function. So anyway, guys, I'm gonna conclude today's lesson